thank you so much to Jamie for having me here, and for all of you to drop by. It's always been great fun to talk at the BJ Foundation's meetings, and I hope it will be at least as much fun, maybe even more. But oh, actually, I should say this will be very fun for me, but maybe less fun for you, because I should give two caveats. The first is that this is very, very much work in progress. I think this is actually maybe kind of like half-baked progress. It's the first time I'm kind of talking publicly or semi-publicly about this. So there may be a lot of kind of silly things, and in some cases I will not go into as many details as you would like, but I think this is because of the nature of the material. But please consider anything I say as just kind of like a starting point for a discussion. And if I'm hopelessly confused, then just do not hesitate to tell me. And I'm also happy for us to, I think, have discussion like during the talk. But otherwise, I will aim for something like 40 minutes, right, Jamie?
Shorter if you can manage it, but 40 it will be fine. We just have to get to the colloquium afterwards. So.
Right, then the colloquium is exactly
at the discussion.
Yeah, the colloquium is exactly at 5 or 11, depending on time zone, right?
Exactly.
Gotcha. Yeah. All right. So yeah, so this is the first caveat. This is work in progress, so it will be very fun for me. I hope it will be also somewhat fun for you, but no guarantees on my end. And the second caveat is that in general, this is a joint work with the Islamco, but between me kind of like committing to giving this talk and the current moment, we didn't sort of manage to coordinate about my and Dennis's view on this stuff. So I guess I should say that all of the kind of good things that you're gonna hear are on Dennis's side, and all of the errors and silly statements are kind of like purely my responsibility. Which I guess is just a more convoluted way of saying that this is very much work in progress. Right. So so I want to talk about parameterized formalisms, parameterized searches, and eliminative reasoning, and all of this, of course, in the context that interests us most, which is the context of observations and evidence, the observations and empirical evidence that kind of allows us to constrain sort of the space of possible alternatives to general relativistic black holes. And I think the plan for this talk is, maybe I will actually just go into the presentation mode. Yeah, I guess it's more convenient that way. And hopefully you can see it a little bit better. So the plan is that I will say first, I will state some sort of general things about eliminative reasoning. And then in particular, at this stage of the talk, I will state a sort of what one may think of as kind of epistemic ideal of eliminative reasoning, and that will be the ideal that takes the form of something like a parameterized formalism. And I will sort of sketch the reasons why one might naively think that this is ideal, and at least when I started thinking about these issues, I certainly thought that this is the kind of epistemic ideal. And then what will happen is that I basically got myself depressed by thinking about this ideal, because I think it will turn out that this ideal is not so ideal. And I will kind of try to show why I arrived at the view that actually this ideal that I really, really loved, and I thought it's a great idea, epistemic ideal at first, may not be so ideal, by kind of looking at some, very briefly and not in depth at all, at some of the kind of alternatives and some of the ways that some of those alternatives to black holes and are kind of explored and constrained in black hole astrophysics. And then I will sort of go back to the initial ideal and kind of consider how to think about it more generally, and therefore also what kind of results we could or should expect for something like eliminative reasoning over parameterized spaces, kind of like anytime soon. So I guess there is no better way of starting a talk on eliminative reasoning than by quoting what Sherlock Holmes said to Watson in the short story The Sign of Four, where Watson says, where Holmes says to Watson, when Sherlock says to Watson, "How often have I said to you that when you have eliminated the impossible, whatever remains, however improbable, must be the truth?" And so I think this is very often the attitude one takes in the sort of situation of eliminative reasoning. We have a set of hypotheses or a set of alternatives, and we kind of try to, if a set is, and we try to rule them out sort of one by one, and whatever remains, however likely or unlikely, that kind of doesn't really matter for us, is the preferred hypothesis. I think maybe a nice sort of quote to show in this context is it's of course it's from a textbook on active galactic nuclei. Of course, it's from 1997, so this is like ancient history by now. But I think Peterson, who's the author of the textbook, says something kind of interesting. So from his point of view, and again, remember this is 1997. He says that after kind of describing the what I think we now consider to be the standard model for the AGN central engine, which is based on the black hole, and he says that this model has a high degree of plausibility, but it remains unproven by any reasonable scientific standard. And again, this is 1997. And he says, the wide acceptance of this model is at least in part due to the absence of serious contenders. So this sort of reasoning seems to very well fit kind of the story of let's look at all of the alternatives, eliminate those which do not work out, and whatever remains, however improbable, must be the truth. And in this case, it's however improbable part is the black hole model for the AGN central engine.
So it's not so much that what remains is not improbable. I mean, there is a degree of plausibility already there.
Sure.
There is evidence in support. It's just not, it's not conclusive as in circa 1997, right?
Yes.
So I wouldn't say that it was an improbable model. However improbable it was, you know, that's what remains.
Right. Yes. So I guess I agree, and indeed, this is what Peterson will say, kind of like at the quote that I put in here. He sort of states that, oh, actually, in recent years, some sort of stronger evidence for the existence of these supermassive black objects emerged, and he mentions some of those like early measurements of M87 using gas tracing. This is before those like S2 kind of bright tracers. So of course, Peterson admits that there is some sort of like positive evidence incoming. And I think if we, I don't know if Peterson is still alive, but of course, if we ask him today, I think he would give us a very different story. And I guess you're right. There's this however improbable part of the Sherlock Holmes quote that doesn't really work well in the context of those models. But the argument is sort of, I guess, you know, if you really start to press me on this, I would say, however improbable as any probability, kind of maybe it's even like maybe 0.8 also, to some extent. I guess what I would say, once you have eliminated the unlikely outcomes, whatever remains, whatever is probability measure, must be the truth or must be confirmed in some sense. I guess I could, if you really pressed me on this, I would sort of try to reframe this motivating quote from Conan Doyle in that way.
Okay. Yeah. We can come back to that later. I should let you proceed.
Yeah. But so sort of this kind of issues about numbers, aside, because I think Priya is right with pressing me here. Mm, what I think sort of happens here is the way that Peterson describes this is that this is something like eliminative reasoning. We have some hypothesis, let's say the black hole hypothesis, and a number of other hypotheses, and sort of what happens is that we have all of this wide variety of various models that are kind of designed to account for the energy output of quasars, but most of them, after a while, tend to sort of fail to account for this or that characteristics of AGN, and so they're physically untenable. So we eliminate them from the kind of space of viable possibilities, and at some point we're left with one or essentially one model. As a matter of fact, Peterson has one sort of, in this textbook, he says that there's one class of models that he considers to be not entirely ruled out, but maybe not very plausible. And he also states that there is the stronger positive evidence, as I said, using M87 observations. But the sort of basic argument here takes the form, I think, of something like eliminative reasoning. We take the set of possibilities, eliminate a lot of them.
Sorry, Julius. So, so I want to understand. So, in eliminative reasoning, right, in the setup itself, do all the hypotheses have to be on the same footing to start out with prior, and then you eliminate those, or is it okay if one hypothesis is already more plausible? So, you know, they're not equally weighted possibilities to start with, right? The equally probable outcomes. Does the framework of eliminative reasoning require the condition that the multiple hypotheses are all on the same footing and equally likely to start with? So the dive is not favored to start with. Or is that not a concern of the eliminative reasoning framework?
That's a good question. I would think that if we require that kind of like our distribution is sort of flat over the space of possibilities, that would be a way too strong of a requirement. So I think ideally what one would do is one would sort of set this up as a space with, and have some sort of distribution, maybe like our distribution of priors. And then we would be kind of like getting new evidence and try to conditionalize on that evidence. And one should kind of be flexible about what priors one considers. So maybe someone's priors would be very high on the GR side, and you know, with some additional peaks for particular classes of exotic compact objects, but kind of very low for naked singularities, and another person might hit vice versa, and so on.
So I think that the initial prior distribution need not be uniform. It can be weighted already. Okay.
I think in practice it should, and I think it would be way too strong requirement for all of them to be kind of considered to be equally likely. Especially if we try to use this as a sort of representation of how scientists kind of actually go about testing these models, right? It would be a way too strong requirement that all of you working astrophysicists have flat distributions when it or uniform distributions, sorry, when it comes to some sort of alternatives. But there is okay. There is the way you phrased this question when you ask whether all of them should be on the same footing could also be understood as should all of them be on the same sort of level of theoretical description.
Yes,
and I think
meant that too. Yeah, I meant that.
Yeah, and I will sort of go back to this later in the talk, I think. So this will be when I will be kind of criticizing my kind of like naive a priori ideal of eliminative reasoning. This sort of unequal footing will play a role. All right, so when we try to when we set up something like eliminative reasoning situation, this is sort of at least in the philosophy of science literature that I'm familiar with, it's typically constructed as a two-step procedure. So the first is we identify the set of alternatives. So maybe here we consider alternative space-time theories or alternative models or alternative, yeah, whatever. And then we try to use observations to constrain elements from this set. One could have a kind of like more subtle and nuanced setup for this, allowing for what is sometimes called meta-empirical confirmations, or some other things such as non-empirical alternative, such as non-empirical additional arguments in constraining the set, but I don't think this should contain us, kind of concern us here. Okay, so if you think of this as a two-step procedure, first identify the set of alternatives and then use observations to constrain the set. So how to identify the alternatives? And in a kind of like sort of history of 20th century space-time physics, a number of ways of identifying the alternatives have been sort of tried out. So here's how Dennis, in the introduction to a 2017 book, A Theory of Space-Time Theories, presents it. He says there are basically kind of like three ways of that have been sort of tried of coming up with alternatives to space-time theories. So the first is one can try to develop a framework which is so general and encompassing that it can capture all the properties of each space-time theory, or at least a major subset of all space-time theories, and allow us to compare them with one another. So there's this sort of first meta theory, which is never declared as one, but might be implicit in the work of the great physicists Weil, Eddington, Einstein, Schouten, and so on. And there the idea is to focus on the underlying geometry on which GR is based, so the Riemannian geometry, and to find new geometries that are generalizations of GRs, on which in turn more general physical theories can be based. So examples of that include the Weil geometry, where we have kind of like independently defined metering and connection, and we weaken the compatibility condition, or maybe we have only an affine connection, or maybe we do not require that the space-time metric mu is symmetrical, or the connection is symmetrical, or we do not require that they're compatible, or maybe we allow additional torsion term in the connection. All kinds of theories like this. So this is like a very kind of like high level framework for comparing space. Another, sorry?
I don't know, you just froze for a second. I thought we finally had our disaster, but you're back, so it's all good.
Oh no.
You said that the alternatives were then constrained by observation, but I think as you've indicated, some of those constraints could be purely theoretical. It can be based on symmetries or other theoretical things that we want from a theory, right? Isotropy,
right.
Whatever else we might assume, not naturalness, not fine tuning, and so on.
Right. So I'm happy that you folks are asking these questions, because this means that you're sort of like a few steps ahead of the slides that I have here. But you're also kind of like foreshadowing what's going to come.
Okay.
So in short, I will like this will I think this will play a role in the argument later, that we in sort of many since you foreshadowed this, I may just as well say it. I think what happens in many kind of like parameterized or systematic searches is that the parameterizations can concern very different level of theoretical descriptions and build around very different things. And this in particular will mean that the kind of like naive ideal that at least I try to entertain in my head is just epistemically not viable. Right. So Dennis continues by pointing out that in the 1950s and the 1960s, more and more alternatives to GR were found that kind of like GR were based on pseudo-Riemannian geometry. So, and here the main difference to GR lies in the fact that we have new gravitational fields in addition to the metric tensor, and maybe not necessarily related to geometry, different field equations, different coupling structures, but ultimately we still have kind of nice Lorentzian setup. And so this is kind of another it's also a very kind of like theoretically grounded set of alternatives. We start around GR and sort of try to modify it, but we modify it in a sort of different way than in cases where we try to allow torsion or do some other drastic changes to the geometry. So these are sort of like, these two are kind of like first types of broad frameworks of comparing space-time theories. And I think in the context of eliminative reasoning, they're interesting and important insofar as kind of when we try to set up eliminative reasoning situation, we want to know what the alternatives to whatever it is that I'm looking at are. And so this sort of modification of theory at a very high level are one of possible sources of alternatives. So in other words, if we start with a conversation about I don't know, such a star data, someone could in principle come and say, oh, I wonder whether my favorite modified gravity theory in either this kind of like pseudo-Riemannian sense or in this like very broad older sense could account for those observations. And so in a way, those might in principle be sources of viable alternatives. But there's also the second kind of meta-theoretical approach to space-time theories, in particular theories of gravitation, where we do not aim to capture all of the properties of given space-time theory. We're only interested in how it behaves in a certain limit. So there may be all sorts of complicated things happening, connections with torsions and additional matter fields and all of that. But we may only be interested in something more tractable, how a particular theory from this kind of like high level description behaves in certain limit, for instance, in the limit of tests that could be carried out within the solar system or with some type of cosmological observations. This is sort of the second approach where we want to look at properties of space-time theory, not in general, but only in kind of what can be experimentally or observationally discerned in a certain limit. This sort of underlines underlines parameterized formalism, such as the parameterized post-Newtonian formalism. And so in parameterized formalism, the situation, I think, becomes much more concrete. So we have some restricted but well-defined domain. In PPN, this is weak field limit, and we want to work with solar system tests. So there's this observation well-defined domain. And hopefully it turns out that the phenomena in the domain can be covered using kind of like, or can be represented using small numbers of explicitly defined parameters. So for instance, the PPN has basically, well, kind of depending how one sets up, but in the kind of like orthodox presentation, by which I mean to be Clifford Will's second edition of Clifford Will's book, we have 10 parameters which represent things such as how much space curvature is produced by unit rest mass, how much gravity is produced by unit gravitational potential energy, how much gravity is produced by unit pressure, and so on and on. And here the thought is that any alternative to GR determines values of those PPN parameters, and of course GR does as well. And this this can and should be explicitly calculated for any new alternative being proposed, because I think the set of alternatives is kind of like typically not fixed ones, and for all people come up with new modified gravity theories, and that's totally okay, as long as when those theories are kind of like mature enough to get tested, we can sort of consider or at least if we think that something like solar system tests can tell us anything about those theories, then we should be able to express their difference between GR in terms of the values of some of those ppn parameters. Okay, so I said that this is an a priori ideal of eliminative reasoning, and you could ask, well, you could have many questions at this stage. The first is there anyone who actually says that this is kind of like ideal of eliminative reasoning? And I think I will be able to find some people in the literature who commit to that, but I haven't, and I don't have them on the slides. But at the very least, I think when I started thinking about parameterized searches, this was an ideal for me. And it was an ideal for me because it is, I think it's a neat way of going about eliminative reasoning, right? We have well-defined domain. We know what parameters are of importance in this domain. So this is a very systematic thing. And we kind of go, if we go around measuring this parameters, then I think that makes a very kind of like exhaustive search possible, of course, up to measurement uncertainties. And I think in a way, one could, if we try to think of this as here are 10 parameters and I'm going about measuring them with up to some confidence level, if I sort of like plug in my priors but distributions of those parameters, then in this way, kind of like the level of confidence in the values of measured parameters implies my level of confidence in the elements of the set of alternatives. It should say alternatives rather than possibilities, right? So in other words, if my prior distributions are a bit for GR, very little for a number of modified gravity theories, and a lot for some other modified gravity theories, and I measure the ppn parameters and they turn out to prefer the GR, then I should correspondingly kind of conditionalize or whatever, decrease my level of confidence in that particular alternative. And so, yeah, so to me, this seems like a good, this seems like the best case of setting up eliminative reasoning. It's systematic, it's exhaustive, and it's also a kind of like very procedurally sort of clear what is happening here. And so, of course, there are also other parameterized formalism. So, for instance, there is a kind of like similar and in a way inspired by ppn framework for testing deviations from GR in cosmology, so-called parameterized post-Friedmanian formalism. All right. So, now, when I say that, to me, at least personally, but I think it's not just me. I think it's kind of like many other people, at least in the philosophy of science literature, who, if you ask them about what's the kind of like ideal way of going about eliminative reasoning, they would describe something like this. Small domain, small number of parameters, and kind of everything that I'm interested can be mapped onto values of those parameters, and then I can kind of like exhaustively search or eliminate them up to sort of arbitrarily levels of confidence. So I think it's a, in a way, this is an ideal that not just like past me, but also some other people might hold. So, and I think it's certainly an ideal in the sense that this, when we're dealing with a ppn, it's a very comfortable epistemic situation. We know exactly what to do in the context of that domain. So it is the kind of ideal in the sense of being kind of very convenient and making you happy. But it could also mean, when we use the word ideal, it could also mean something like a a normative ideal, right? So what it would mean is that having something like a parameterized formalism is the most appropriate way or desirable way of conducting eliminative reasoning. And so what that would mean for me is that if I want to do eliminative reasoning about black holes and kind of like eliminatively ruled out alternatives so that for Watson only black holes remain because you have eliminated all of the alternatives, I should want to construct something like parameterized post-curve formalism. I guess some people are already using this phrase, but something like that. So it should be built in some way around this curve spacetime. It should parameterize the possible measurable deviations from it using small number of parameters. And I think also it would be nice if various possible observations that test the hypothesis that black holes in our universe occur could be kind of brought into a single framework in some sense analogous to the parameterized post-Newtonian formalism. So I guess what I'm saying is that there are two senses, which is something like PPN could be ideal. It could be something that's great to have and makes you happy. And of course, I think no one would debate that. But it could also be ideal as an ideal of eliminative reasoning. And then it has this kind of like normative aspect to it. And then I should, in the sense that this is something that one should build for eliminative reasoning about black holes. And I surely thought so. So at least it's kind of like a psychological story of past me. But I think it's not just me. So in a way, it's more interesting than just me being confused, because this is a normal occurrence. And in any case, I got my stage of something like that would be the ideal of eliminative reasoning. And now I think this ideal might be tempting, but as a matter of fact, we might be better off not pursuing it. So as an epistemic strategy, this ideal might be less than ideal. And so in particular, maybe we should not spend effort on something like a PPN version of tests of black holes.
May I just say something on the last slide? So this has been attempted, and there are various parameterizations on the market that use this sort of thing for strong field tests of GR with, for example, the Event Horizon Telescope or LIGO and so on. And the issue there is that all of these, so if you consider a large number of alternative theories, they also admit the curve solution as a solution. So when you modify away from GR and try to use those constraints to constrain the curve spacetime, you get no constraints basically on alternative theories. So this is another issue, that in some limit, all of these other theories admit curve as a solution. So even if you had a parameterized test, you may not be able to rule them out within such a formalism very straightforwardly. You would have to look at tests that sort of
tests on multiple domains.
Right. So for example, with the EHT, the problem is that you just have one observer, which is the size of the shadow. And this does not allow you to test.
Yeah, it's not enough of a constraint.
Enough of a constraint. So LIGO may be more constraining, but the sort of formalism has to test various aspects at the same time.
Right. So I think the point that Prashant is making, and I agree with them, if the alternatives all asymptote in some limit to the same thing, then that's a real limit of, that's a very limiting case, right?
Yeah, and also, like, for example, different theories like have different characteristics in, for example, when they radiate gravitation waves, they may do that differently, but they may have the same curved black hole spacetime at the same way, but they radiate gravitation waves differently. So you need to use the same framework to be able to test the image of a black hole and also to test the built templates of gravitational waves.
But I mean, doesn't this just say that the shadow by itself is not enough to discriminate between the alternatives, right? So
that's true, but you could try to build different data points using different observables, but you still need the same framework to be able to compare these different tests.
I'm confused because I always understood these parameterized tests as being, okay, so we're building this sort of parameterized framework and we have these different parameters, and the different parameters in some sense correspond to alternative theories.
Not always.
I mean, not in the direct sense that like if you get this parameter, that this parameter's value is favored, that you know that it corresponds to some well-developed theory, but simply in the sense that if your evidence is pointing towards the sort of null value, which
Yeah.
would correspond to GR or Kerr or whatever, that you have evidence that some alternative
Yes.
theory corresponding to it is the right one. And so I guess I'm just confused as to why you couldn't do eliminative reasoning in that way. Like, I understand that certain kinds of observations would be insufficient to provide constraints on the parameterized framework, but that seems like an issue of the observations rather than the framework necessarily.
So, for example, yeah, that's an excellent point. So, null tests are the way that things have been done so far. But consider a theory that has Kerr as a solution, but it casts, for example, like it casts the same shadow, but it has different gravitational wave aspects. So when you do a test with DHT, it will pass a null test. But then when you do a test with gravitational waves, that should fail that test.
Right. So you're saying,
You need to have the same formalism to be able to test this aspect of the theory and the radiant
Right.
aspect of the theory and so on.
yeah, so I thought that what Juliusz was suggesting was that a situation where, if you get like the null result,
Yeah.
that doesn't guarantee that your theory is correct.
Right.
Or that GR is correct or whatever, but rather if you have lots of different parameterized tests, and in any of them you get evidence that is a non-null result,
Right.
it would be some evidence for
Mhm.
an alternative, and so presumably you need to do lots of different things.
Right. Or I could also be a kind of like we of course we try to not do these things these days, but I could be like imperialist. I could say, oh, here are all of those parameterizations that you're using, and we should put them all into a joint single formalism, right? Because ultimately I'm kind of like looking at black holes, my leading hypothesis that all of them occur, and so I should have something like a single formalism that can parameterize both shadows observations and some gravitational wave observations. And maybe kind of like some of the regions of that parameterization would be insufficient to rule out some of the alternatives, like with the shadow observations that you mentioned. But then maybe I could constrain kind of like that region of parameter space using other set of observations, say gravitational wave observations, and kind of in that way eliminate some of them, kind of like within a single framework, because ultimately I would like to, I might want to translate or kind of like move between, the constraints from gravitational wave observations and constraints from the shadow observations.
I should also say this because you mentioned it. This is exactly what has been done in recent times. All of them do different parameter tests with different schemes, LIGO, EHT, etc. And all of them
Right.
translate their the constraints on the parameter spaces that they get onto the PPN parameter space, and thus they compare between each other. So this is what has been done, and at least this has been done. So
this is great. Do you think that this sort of work or framework is in many ways like the PPN, or do you think that it differs in some important respects?
I think that there's not, like with these strong field frameworks, there's not a clear idea. Like for example, in Will's Thorne and Will in all these papers, they sort of indicate that these three parameters change, then this means a violation of, for example, the weak equivalence principle or things like that. There's specific things that they're tied to. I think that physical whatever the substructure below these strong field parameterized frameworks, I don't think that exists so far. Because they're just, for example, if you have a metric function and you deviate away from, say, Schwarzschild or Kerr, then how much can you deviate away? So these really are focused on null tests, and this is not developed. What it means physically for a parameter to be varying in this way, that's not, there's no clear insight into that. So in that way, they're different from the PPN formalism, but they're still they're excellent for null tests, for example.
Yeah.
Okay, perhaps we should
This
let Juliusz
is
continue just
right.
'cause
We are
This,
gonna
no,
run out
this
of
is
time.
this is very interesting, but it also makes me kind of like kind of revert to my past belief that something like a single parameterized formalism might actually be a good thing or viable thing. So I should continue as long as I kind of like do not convert to my old beliefs entirely. So I guess what I want to do now is I will kind of like take us through just like I think like 5 different sort of parameterizations or other constructions of the set of alternatives, and in some cases parameterizations, but very often parameterization will be not be kind of like a distance measure or anything like that that we use in black astrophysics, and then conclude. So I think the first thing to be said is that, of course, if we have some parameterization, it does not have to be a parameterized formalism to the same standard as a PPN, right? We could just conveniently parameterize some subregion of alternatives without pretending that our parameterization kind of like fully and exhaustively parameterizes all of the alternatives in that domain. I think this is what sort of happens when VHT runs, for instance, this very expensive GRMHT simulations. This is kind of like sparse sampling of, in a way, of only those regions of parameter space that are kind of like interesting for modeling particular sources. So that that form of parameterizing alternatives does not have to be exhaustive in any way. And eliminative search does not have to be parameterized, and also it does not have to be systematic. And I think this, for instance, happens in the M87 paper 4. But I should say first that I think that most of the parameterizations that I will look at, in a way, they are about figuring out whether the same hypothesis, which is isolated black holes in our universe, are subextremal occur. So these parameterizations try to test one and the same hypothesis, but they do test this in a different way. So you may be worried, oh, is this comparing apples and oranges? Some of them will be about gravitational wave searches, some of them will be about shadow observations. So is this comparing apples and oranges? And I guess what you just said is kind of like maybe a better argument than the one I had against this idea that this is apples and oranges, and they're, but the way I would put it is that, or at least another argument is that, well, some of those alternatives concern compact objects of any mass, and some may be viable in context of supermassive black holes and some of the gravitational wave detections, but some of those alternatives, such as exotic compact objects, do translate to both of the echos and shadows observations, to gravitational wave observations through echos and shadow observations with additional surface brightness. And so it is kind of like proper, and it makes sense to think of them in a kind of joint way and unified way, at least at some level of abstraction. Okay, so now a few of the parameterizations. The first is we could do it at a very high level. We could have a landscape of modified gravity theories. We have Lovelock's theorem that tells us that the Einstein's field equations are unique, and so we could construct modified gravity theories by violating premises of the Lovelock's theorem. This is one kind of way of systematically constructing alternatives, although maybe not necessarily parameterizing them. I will speed up a little bit so that we have a few minutes of discussion, so I'll try to wrap up in 5 minutes, but please ask me for details or email me afterwards. The second is we could consider something like the set of different ways of constructing the horizonless objects, which in a way behave up to some precision in the same way as black holes. So in this context, we have, for instance, the Buchdahl's theorem that tells us about kind of how massive a compact object can be. And again, it's a theorem, kind of like in the Lovelock's case, it's a theorem that has premises, and so violations of those premises can be used to construct various models of particular sources, so something like black hole mimickers. And so this is maybe not a parameterization, but this is, well, it may be a parameterization, right? I have a theorem, I have premises, which premises are violated, I parameterize the set of alternatives in that way. Another parameterization is of what is sometimes called parameterized post-Einsteinian framework, where we basically expand the gravitational wave templates by piecing together waveforms in such a way that sort of like additional non-GR effects can be allowed. And there's a really nice paper by Lydia Patton, sort of on the philosophy of these models. And this, I think this, it's important to point out, as some people do, but this PPE is a bit different than the PPN or PPF because it's a parametrization of observables. So what can I see in the gravitational waves rather than theories themselves, like it was in the case of PPN, where I have particular modified gravity and it translates into one of the 10 PPN components. And finally, we have things such as parameter surveys on that the EHT does, where we have a bunch of models. Some are heavily theory-based, like GeoMHD ones, and some may be, just like sort of simple geometric models of the source, and we use this as this kind of space of models as kind of the relevant set of alternatives to consider in those observations. And finally, EHT is also doing something like eliminative but not very systematic reasoning on the set of other alternatives. So this is a kind of like eliminative reasoning, which is not in a way parameterized, partly because as that paper states, I think this is from M87 paper 4 or 5, the top of my slide is cut off, so I can't see it very well. Each of the many exotic alternatives to Kerr black holes can span an enormous space of parameters that's only poorly constrained. So these comparisons are at best or should be considered preliminary and not in a way like kind of like systematic and so kind of like conclusive and exhaustive, like something like PPN. All right, so that was like a very brief tour through just some of the ways of constructing alternatives to either black holes or some of the properties that we have in GR. And I guess it's highly incomplete, and especially in the EHT case, like very different ways were sort of like bundled into one. So you could object to the presentation, but I think you won't object to the conclusions that I will now make. But maybe it's a good moment for to ask if I kind of like completely lost all of you or not yet, or if there are any other questions at this stage.
No, carry on.
Perfect. All right. So now I think we're in the following situation. I told you what is my kind of like naive ideal, and I took you through some of the kind of like parameterizations and way of constructing alternatives. And I now have the following issues with my ideal. The first is, can all of those parameterizations fit into a single framework? And I think they can't, because they kind of, many of them concern different levels of theoretical description, right? Some of them parameterize theories, like the modified gravity theories. Some of them kind of parameterize models constructed from, in a way, from a particular solution, like exotic compact objects. Some of them parameterized observables, such as the size or shape of the shadow or PPE framework. In some cases, the set of alternatives is sort of not very well defined and remains underexplored, and is maybe even hard to parameterize. I think it's a good example of that exotic compact objects, which, for instance, do not, many of them, I don't think there are many models of them with spin, for instance. So it's a kind of like underexplored set of alternatives. So I guess the upshot of this is that it doesn't seem likely that those parameterizations can fit into a single framework such as the PPN. We could maybe translate between them in some ways, but there seems to be little hope of just putting all of these things in a single framework because they concern so very different things. But I think that's a good thing. Many parameterizations can be a good thing because we can sort of use one to rule some region of theory space, and then we don't have to even bother with extracting predictions from some other subregion from the parameter space. Maybe a good example of that is the neutron star merger, GW 170817. It has electromagnetic follow-up. We can use it to rule out some alternatives to GR. And so from this point of view, there is no need to even think about extracting shadow parameters from Teves or biometric theories, because we have other parametrization, and we don't even need to bother about sort of extracting some of the other predictions from another theory. And if we had some single unified framework such as PPN, then I think one would be morally obliged to also extract those predictions. And in the light of the merger, that would be basically a giant, well, that time could be better spent. And so I think from all of this, it follows that this ideal that I had may not be very ideal. Many parametrizations may be a virtue, kind of analogously to Eric Curiel's work on many definitions of black holes. And why they're a virtue? Because multi-level relationships make it very hard to construct a single parameterized formalism. Extracting predictions from some of the alternatives might not be useful. And also sometimes including all the alternatives might not be very useful, and so which would be a problem for the completeness. So for instance, no one wants to go back to the 60s and include all of those older ruled out alternatives into a single parameterized framework. But if the framework has a pretense of being complete, then one should, I guess, in principle do that. But of course, that would not be very useful. Okay, and I think, so let me wrap here so we have at least a few minutes for discussions. I think all of those features suggest that kind of like my initial expectation that I should have something like analogous to PPN for black hole searches is just not a very good epistemic ideal, because there are all of these good reasons why having many independent and subtly overlapping parametrizations may be a good thing, and constructing a single framework might be kind of detrimental and not the optimal use of research time. So in the sense, I guess, my naive epistemic ideal might be less than ideal. I think that's it.
Yeah.
Okay, remove pin so we can get everyone on Zoom. Questions?
So a quick question, to the point in the last slide, what does it mean, old alternatives? Like old alternatives that have not yet been ruled out and are somewhat compelling, or old alternatives just for completeness of, classes of explanation? Can't hear you.
Can't hear you. 1 second. Maybe I.
Oh, sorry. No, that's my fault. Overdetermination. No, I meant alternatives just for the completeness sake.
Okay.
Yeah, of course, if there's some alternative that we still consider relevant, then it should it should be tested in some way. But I thought that one of the advantages of something like PPN is that we have kind of like complete control over the domain, so to speak. Right? And sometimes
there's an interesting side to, I mean, Priya's been getting at a certain point in various ways in her comments here, but sometime, not now, it would be interesting to discuss when we put forward theoretical alternatives simply for the purpose of elucidating by contrast the import of a particular theory. Experimenters do it, they like to be able to say, well, this favors X theory rather than Y, so if Y doesn't exist, they come up with it, which sometimes feels like a stalking horse rather than, a vibrant theoretical alternative. But it does do something. That's why we keep coming back to filling out the space of theories. So sometime we should investigate the purpose of such alternative formulations.
As always, Peter frames it better than I could have said it.
Yeah, I wonder if also what Peter's pointed to here is that there seems to be much more, in your sort of naive picture of eliminative reasoning, it was this two-step thing. But perhaps in reality, it's this just constant evolving, you eliminate some things, and then you're creating more alternatives as you go in this kind of growing cycle.
Right. Okay, so I had one last slide on this, and I fully agree with these comments. My naive ideal was just not very good, though I think it might be compelling. So there is something to be learned maybe from criticizing it, especially if other people commit to the ideal. But I also I think this also tells us something about the ambitions of those models and what we can expect. So, for instance, I won't name names here, but I've heard some people from the HT being kind of frustrated after the M87 papers were published, because in those papers one can to some extent sort of rule out some naked singularities models and some wormholes and some of the alternatives. And some people were sort of frustrated sometime later when it turned out that, oh no, like other people constructed wormholes and naked singularities or whatever the class of models that sort of, from the perspective of that person from the collaboration, those models were kind of like already ruled out by what they did in the M87 papers. But now all of a sudden there is this proliferation of new models. So there was a certain degree of frustration in the conversation present. I thought we ruled them out, but here people are coming up with more and more of those models. And I think it's just natural. It's something to be expected if we're not working in, in something like a PPN kind of exhaustive eliminative search. So I think this sort of more kind of like fluid, time-dependent, more contextual set of alternatives also. I think the person might be less frustrated if they think of eliminative reasoning in this way rather than in a kind of like very strict and conclusive and exhaustive way.
Okay, well, I think we're pretty much out of time. So let's thank Juliusz again.
Thank you so much. And yeah, drop me an email if I said something absolutely egregious or missed an interesting reference. Thanks.